Chemical compounds can be taken apart into chemical elements. If you're taken apart in the same way, then over 80% of you consists of the elements carbon and oxygen. I'm going to use those two elements to introduce the idea of atoms. You saw oxygen made from water in video sequence 2. Now I'll make carbon from sugar.
I've put the sugar into a cork test tube. The cork carries an exit tube that dips into water. So, when I heat the sugar, the heating will occur in a confined space and the sugar won't burn. Instead, it decomposes to charcoal. Sugar starts to melt first. Now you get that cream caramel colour. Lots of water is given off as steam. It starts to darken. And so if you're stuck for charcoal at the barbecue, this is the way to make it.
Charcoal is nearly pure carbon. By burning it in the oxygen of the air, I can make carbon dioxide. And carbon dioxide can also be made by the reaction of acids with limestone. To emphasize that it contains carbon and oxygen, I'll take it apart. And I'll start with carbon dioxide that's been cooled until it turns solid. Dry ice.
Here's a block of solid carbon dioxide with a hole drilled in the top, and alongside it a bunch of magnesium ribbon. I'm going to start the magnesium ribbon burning by heating it in a flame. Now once it's going, I'll put the dry ice on top of it, and you can see that the magnesium continues to burn in the carbon dioxide. When I remove the block after the reaction, there's a mixture of white material, which is magnesium oxide, and black particles of carbon, which have come out of the carbon dioxide.
Magnesium is very unusual in burning in carbon dioxide. Most things don't. What's more, carbon dioxide is very dense and it doesn't burn itself, so it hugs the ground and puts fires out. Here's a demonstration.
These candles are burning in a sloping perspex gutter. I filled this tub with carbon dioxide. The dense and invisible carbon dioxide creeps slowly downwards along the bottom of the gutter, and as it goes, it snuffs out the candles one by one.
So carbon and oxygen react to form a gas, carbon dioxide, which is very dense and puts fires out. But it isn't the only gas which can be made from carbon and oxygen. I can show you that by passing carbon dioxide over very hot carbon.
It's this carbon that's going to react with the carbon dioxide. I want plenty of it, so I'm going to use 2 boats. The tube is made of silica because it's going into a high temperature furnace. The reaction goes best at about 1000 degrees Celsius. The soda-lime tube removes the surplus carbon dioxide. The carbon dioxide going in is used to put fires out. The gas coming out burns with this beautiful blue flame. So what do you think it is? It's carbon monoxide.
Carbon monoxide is also a deadly poison. So carbon and oxygen can combine in 2 possible ways. In both cases, the product is a colourless gas. But in one case, the gas is dense and is used to put out fires. In the other, it burns and is very poisonous. It's fascinating that the same two chemical elements can give two such different chemical compounds. But what I want to concentrate on is their chemical compositions. Suppose I start with 3 grams of carbon. Then I find that it takes 4 grams of oxygen to turn it into carbon monoxide. But if I turn it into carbon dioxide, it takes 8 grams of oxygen. Now 8 is twice 4. It takes exactly twice as much oxygen to turn a particular mass of carbon into carbon dioxide as it takes to turn it into carbon monoxide. What could be the explanation of this simple ratio?
Suppose we make carbon monoxide by starting with 3 grams of carbon. Then we find we need 4 grams of oxygen to do it. In chemical reactions, the mass doesn't change, so our 3 grams of carbon and 4 grams of oxygen will produce 7 grams of carbon monoxide. Now suppose we make carbon dioxide from 3 grams of carbon. This time, we find that 8 grams of oxygen are needed. And so 11 grams of carbon dioxide must be formed. Now the 8 grams of oxygen in the second reaction is exactly twice the 4 grams of oxygen in the first. Why is this? Let's begin again with carbon monoxide. Let's suppose that carbon consists of tiny particles called carbon atoms, and oxygen of tiny particles called oxygen atoms.
Now our 3 grams of carbon will contain a certain number of carbon atoms. That number is enormous and makes the arithmetic impossible. But the argument that I'm using can be illustrated by any number. So I'll use 4. Let's imagine that 3 grams of carbon contain 4 atoms.
The atomic theory that chemists use claims that atoms are never destroyed in chemical reactions. At most, they just get new partners. So the 4 atoms in our 3 grams of carbon must still be there in the carbon monoxide.
But in carbon monoxide, those carbon atoms have got new partners. Those partners can only be oxygen atoms. So let's suppose that each carbon atom teams up with 1 oxygen atom.
So 4 oxygen atoms are needed, and they must have come from the 4 grams of oxygen. So the 3 grams of carbon and 4 grams of oxygen that combine to form carbon monoxide contain the same number of atoms. Now we turn to carbon dioxide. Again, I've put 4 atoms in the 3 grams of carbon. What about the oxygen? Well, if there are 4 oxygen atoms in 4 grams of oxygen, then in 8 grams of oxygen there must be 8. What does this mean for the carbon dioxide that's formed? Well, atoms are not destroyed in chemical reactions, so the 4 atoms in the 3 grams of carbon must also be in the carbon dioxide. But so must the 8 atoms of oxygen. Now these partner the carbon atoms. As there are only 4 carbon atoms for 8 oxygen atoms, each carbon atom takes 2 oxygen atoms.
Let's summarise. We start with an experimental observation. This tells us that in carbon dioxide, carbon is combined with twice the mass of oxygen that it's combined with in carbon monoxide.
Now we assume that the particles or molecules in carbon monoxide consist of atoms of carbon and oxygen combined in a simple ratio, say 1 to 1. It then follows that the particles or molecules in carbon dioxide also consist of atoms of carbon and oxygen combined in a simple ratio, 1 to 2. What's true for one gas is true for the other. The atomic theory gives us consistent results. But we can go further. We've come out of this with the idea that 3 grams of carbon and 4 grams of oxygen contain the same number of atoms. So 3 grams of oxygen contains only 3/4 of the number of atoms in 3 grams of carbon. What this tells us is that the mass of an oxygen atom is 1/3 greater than that of a carbon atom, but that the mass of 3 oxygen atoms and 4 carbon atoms is the same.
The idea that each chemical element has its own special kind of atom answers the question left from video sequence 2. What is there of red metallic copper and colourless oxygen in black copper oxide? The answer is the atoms of copper and the atoms of oxygen. And we've even made a start on working out the relative masses of atoms. An oxygen atom, we decided, is 1/3 more massive than a carbon atom. But watch out. That conclusion began with a guess. The guess that the chemical formula of carbon monoxide is CO. How can you get relative atomic masses without guessing chemical formulae? It took scientists 50 years to solve that problem. Reading about it will be your next job. Hitler and Napoleon never visited England. They only stared at it on a clear day from the French coast. What they saw was white, the chalk of the white cliffs of Dover. And here's some more of the same, but in a disused Norfolk quarry. At the centre of the quarry is a chemical reaction vessel, a lime kiln. It's a brick-lime pot about 3 meters deep. In there, the chalk, a form of calcium carbonate, was heated and decomposed. This beer glass shows how it was done. The pot was filled with alternate layers of chalk and either coal or coke. Then the coke was lit and the heat of the fire decomposed the chalk. Let's see the reaction for ourselves.
What you're seeing here is the reaction that goes on in a lime kiln, but at a much higher temperature. I'm using a methane oxygen flame and playing it directly onto the chalk, calcium carbonate. The white light that's produced often crops up in everyday conversation. It's called limelight, and it's emitted by a product of the reaction, calcium oxide or quicklime. Limelight appears when quicklime reaches a very high temperature. So, when you heat calcium carbonate, calcium oxide or quicklime is one of the products. The other is carbon dioxide gas.
Besides the decomposition of chalk into quicklime and carbon dioxide, there was another reaction. The carbon dioxide reacted with hot, unburnt coke to give poisonous carbon monoxide. When it reached the surface, it burnt with a blue flame. So, on a clear winter's night, you can imagine this shimmering disk of blue fire, beside which passing tramps would sometimes try to get a warm night's sleep. Occasionally, so the records tell us, the unburnt carbon monoxide made sure that they never woke up. Now let's go down to the bottom of the kiln. Around the lower part of the pot, there's an underground chamber. Come in and have a look. Here's the outer wall of the lower section of the pot. The surrounding chamber is circular and brick-lined. It also has an arched roof. The diameter of the outer wall is about 7 meters, and there are ventilation holes in the walls. Now look at this square aperture. When the kiln was working, it was covered by a metal grid. Behind the grid, a chute sloped up into the heart of the pot. Once a day, the grid was removed, and the quicklime product slid down the chute and emerged in a shower of dust. Now there were workmen in here, putting the stuff into bags. To protect themselves, they covered their noses and mouths with a damp towel. Even so, they often emerged from the chamber with their noses streaming with blood. Quicklime damages human tissue. I'll show you one of its reactions. This is quicklime, the stuff that's made in a lime kiln. I'm going to add a little water to it. Quicklime is very thirsty. It reacts vigorously with the water and produces something that's commonly called slate lime, or calcium hydroxide. Slate lime isn't very soluble in water, but if I stir some up and filter it, I get this, lime water. What I want to show you is that this lime water, calcium hydroxide solution, changes the colour of litmus. Acids, remember, turn blue litmus red. Calcium hydroxide solution turns red litmus blue. Substances that do that are called alkalis. Calcium hydroxide is an alkali. Any explanation of this word alkali comes from trees and plants, because alkalis were once made by burning them. The word comes from the Arabic, alkali, roasted ash. What I'm going to do is to take some wood ash and add it to hot water. Then I stir and next I shall filter it. As the solution comes through, it turns the litmus blue. Wood and plant ashes are alkaline. Solutions like this were once used to make the glass for medieval cathedrals. If you know the right treatment, you can extract from them two new alkalis. Here they are, sodium hydroxide and potassium hydroxide. We've now got three alkalis: sodium hydroxide, potassium hydroxide, and calcium hydroxide. All three of them eventually dissolve in water. Now let's add the three solutions to litmus: sodium hydroxide, potassium hydroxide, and calcium hydroxide. All three solutions turn red litmus blue.
So, when it comes to the reaction with litmus, alkalis are the complement of acids. Acids turn blue litmus red. Alkalis turn red litmus blue. Now there's a substance, chalk, that reacts with acids to give a gas, carbon dioxide, which is slightly acid. Is there a substance that will react with alkalis to give a gas which is alkaline? There is, and it's called ammonium chloride.
Ammonium chloride was first discovered in the Middle East, in soot from furnaces that had been fired with camel dung. Europeans, being short of camels, resorted to mixtures of salt, urine and soot. Eventually, they found that soot alone was often enough, and that's what I'm using here. I'm just heating it in a loosely covered flask. You can see fumes above the soot, and some nice turbulent motion inside. The surface of the soot is turning white. That's ammonium chloride. It sublimes. That is, it changes straight from solid to vapour. Then, if the vapour finds a cold surface, it goes back to a solid. The ammonium chloride has sublimed up through the hot soot to the cooler surface. I'm steering the white ammonium chloride to the cooler top half of the flask. There's a little bit of tar lower down, but at the top a nice white solid. White ammonium chloride sublimed and separated from black soot. I'll use it to make the promised alkaline gas, ammonia.
Ammonia gas is made by heating alkalis with ammonium chloride. I'm collecting it in this tube. It's arrived at the tube by being passed upwards through this tower of quicklime, which dries it. It's come to the tower from a flask, where I'm heating a mixture of ammonium chloride with an alkali, calcium hydroxide.
Let's go back to where the ammonia is being collected. I put a piece of red litmus paper at the mouth of the tube. It instantly turns blue. Ammonia is an alkaline gas. Ammonia is less dense than air. It pushes the air downwards out of the tube. I'll just put a cover on the tube and take it away. Let's find out how soluble ammonia is. The water rushes in. Ammonia is very soluble in water. Here's a more exotic way of demonstrating that solubility. I filled this flask with ammonia and sealed the filling tubes with rubber teats. One of the tubes is a long one and goes right up into the bowl. I'll invert the flask in a tank of red litmus and remove the teat from the long tube. The liquid slowly rises up the long tube. I'll give it a bit of encouragement. There it goes. The first few drops of liquid that enter the flask dissolve all the ammonia. That creates a vacuum, so the litmus solution fountains in to fill it. When the litmus gets into the flask, it turns blue, because a solution of ammonia is alkaline. But it isn't difficult to turn ammonia back into ammonium chloride. All you need is hydrogen chloride. Here, I'm using the hydrogen chloride released by a drop of concentrated hydrochloric acid on a glass rod. When the drop is put into ammonia, white fumes of solid ammonium chloride appear. Alternatively, I can just put gas jars of ammonia and hydrogen chloride together.
And those white fumes are ammonium chloride. You've now seen three acids: sulfuric acid, nitric acid, and hydrochloric acid. You've also seen three alkalis: calcium hydroxide, potassium hydroxide, and sodium hydroxide. In their different ways, these two classes of compounds are very corrosive. John Haig, the acid bath murderer, put his victims' bodies into concentrated sulfuric acid. Adolf Leutgert, the Chicago sausage maker, put his wife's corpse into hot concentrated potassium hydroxide. But what happens when these two classes of compound are brought together? When, for example, concentrated sodium hydroxide reacts with concentrated hydrochloric acid? I'll show you now, and at the same time I'll read a 17th century description of the reaction. The solutions of the alkali and the acid are in their natures totally unlike, foes and adversaries of each other. And when the two are brought together, and the one has overcome and killed the other, neither a fiery liquor nor an acid spirit is to be found in their dead bodies. What is left is ordinary salt. So concentrated hydrochloric acid and sodium hydroxide, each so corrosive in their different ways, react violently to give the harmless salt that you sprinkle on your fish and chips. The reaction I've just shown you is called a neutralization reaction. The acid and the alkali neutralize each other. But whatever acid or alkali you use, the reactions have something in common.
All of the acids contain hydrogen. All of the alkalis contain hydroxide groups, OH. During neutralization, the hydrogens and the hydroxide groups combine and form water. If that water evaporates, the remaining bits of the alkali and the acid get together to form a salt: calcium sulfate, potassium nitrate, and sodium chloride.
That seems to tidy things up very nicely. But there's one property of acids and alkalis that it doesn't explain. Their solutions conduct electricity. I'll show you what I mean by using concentrated hydrochloric acid.
Here I'm doing to concentrated hydrochloric acid what I've already done to water, taking it apart by passing an electric current through it. Again, it breaks down into two gases. This one, at the negatively charged electrode, is hydrogen. The other one, at the positively charged electrode, is chlorine. You can see that the two gases are produced in equal volumes. Now I'll show you a test reaction for chlorine. I've removed the chlorine tube now. Chlorine has a characteristic reaction with potassium iodide solution. I've put some onto this filter paper and I'll dump the chlorine onto it. A brown deposit of iodine is formed. What this experiment suggests is that the hydrogen and chlorine in concentrated hydrochloric acid are present as charged particles. These charged particles are called ions. The hydrogen ions, which must have moved to the negative electrode, are positive. The chlorine or chloride ions, which move to the positive electrode, are negative. Our three acids all form positive hydrogen ions in water, and our three alkalis all form negative hydroxide ions. In neutralization reactions, the positive hydrogen ions characteristic of the acid combine with the negative hydroxide ions which are characteristic of the alkali. The product is simply molecules of water.
I started this video cassette with water, with waves breaking on a Norfolk beach. I've ended it with a reaction in which water molecules made from atoms are formed from charged ions. Those three ideas, atoms, molecules and electric charge, are three fundamental concepts on which the huge science of chemistry is based. There's plenty more to learn about chemistry, lots of new horizons, but wherever you go, those three ideas will have to go along with you.